EMI issues are closely tied to signal integrity issues, and in this live masterclass, I will show you how to use the electromagnetic simulation software called Simbeor to help us identify signal integrity issues on the board and review problems that could lead to EMI issues and EMC test failures. If you don't know who I am, my name is Dario Fresu, and I'm the owner and founder of FresuElectronics.com, as well as an EMI specialist and record a live class here about watch is part of the Fresu Electronics Academy. So if you're interested in attending a session like this live, join us there. So the software that we're going to use is Simbeor, and we can see the board under the signal integrity perspective. So why signal integrity perspective? Because this is the most important one as it relates with electromagnetic compatibility result. So what the software does is essentially analyze the board in terms of signal integrity, but already this is going to tell us three important things, which are the return and reference plane. Then we have also the impedance discontinuity, and then we have the crosstalk. So three different things, which are the most important things. So if we understand these three most important things, we are already in a very good path to pass EMC test. Now, this is not everything because there is still a lot of things that we have to check. So like the placement, how far are the components? So things like in terms of radiated emissions, conducted emissions, so how the board is placed, how the system is constructed. But these are the first three most important things that we have to check. So as soon as they give us, this is my project that I want you to review it in terms of EMI. So how am I going to perform? Do I have a chance? I don't have a chance. So this is what we can do. First of all, the return reference plane. And this is why it's important to understand that two-layer boards like this one here, they're not going to perform well in terms of electromagnetic compatibility, nor in terms of signal integrity. Because the problem is the signal transmission. How does the signal transmit in here? It's always about the picture that I shared, which is the picture here. So if the propagation of the signal, so how the signal is propagating between these two layers, so the signal propagates at the speed of light within the dielectric in here. So the speed of light in here is going to be almost half the speed of light in space. So the way this one propagates is because we have the signal and the reference. So the electric and the magnetic fields are both established in here. And this is why we have the signal propagation, because both the fields, they change in here in time when the signal is propagating through the structure, which is constructed by the board. So we're not talking about the electrons flowing through the conductor and then going back, or we're talking about fields propagating in between these two structures, which are the signal trace and the return reference plane. So when we have this scenario here, how is the signal going to propagate if I don't have the structure? It's going to try to establish the structure. But the problem is that since it's in between conductors, I can already imagine what is going to happen in here. For example, let's take this part in here. When the signal is trying to propagate from this trace in here, it's not going to go like this and then go through the vias, spread, and reach a point that it has to reach. Because it is not going to propagate in terms of electrons, but it's going to propagate in terms of fields. So the fields, how can the field be established in here? And we're going to see that when we analyze it under the software. So the fields are going to be established between these two copper traces. This is already crosstalk. Also between these copper traces. So it's essentially going to establish a field which goes like this, and then it's spread with the lowest impedance path. So where there is the lowest path of impedance, in order to conserve the energy, not to spend too much energy for the propagation, is going to be established between all these copper structures, but also between the top layer and the bottom layer. So whatever field I try to establish in here, in this point, is going to couple with all the structures that I have in between. In the space in between is going to propagate the signal, not within the conductor. Especially depending on the rise time that I have, is barely going to see the conductor because of the skin effect. It's going to stay outside of the conductor. So it's the field that propagates within. This is all the problem. So I have zero chance with something like this to pass electromagnetic compatibility test. Because once I put the antennas to measure what are the fields that this board is radiating, what I'm going to see in here is all the fields that were supposed to stay within the circuit board. So they were supposed to propagate from one point to the other point between the printed circuit boards. Now, all of the sudden, since they are not contained, they're going to spread around, and I'm going to see them all outside of my board, spreading out. And so if I have the antenna here trying to measure the fields, what is going to happen? I'm going to catch these fields in here, and they're all coming from this printed circuit board. So if I can create the structure that clearly contains all this field, what is the antenna going to pick up in here? Barely nothing. So this is how simple it becomes electromagnetic compatibility. It's just a test of, did you design the board correctly or not? And then when you expand it to the other test is, did you design the system correctly? Yes or no? And it all comes with this. The fields, they have to be contained within these structures. So conductor A, conductor B, they have to contain the fields because the fields are in between the space between the conductors. So that's all we have to understand. Once we understand this, then look, it's gonna become super simple also to understand how am I gonna place the cables. If this is the strategy that I need to use, this is the fundamental strategy that I can use to design printed circuit boards that pass electromagnetic compatibility straight away. So if I have the cables placed in this way, and I know that the fields are in between the cables, so if this is conductor A, this is conductor B, let's suppose if this is power and this is the GND. So how are the fields going to be established between these two conductors? Becomes super simple. If we know that the fields are in the space in between the conductors, around the conductors, then I know that these fields are going to be established like this because they are trying to couple with each other in this way. So look at the fields. If I have an antenna here, what is going to happen? If I have my antenna here, I'm inside the chamber and I'm trying to measure this field. I'm going to pick up these fields. So if instead I place these conductors placed in this way where I have conductor 2 here, now how are the fields going to be established in this way? So if I try to pick it up with the antenna, what am I going to see here? Nothing, because I'm too far from where the fields are spreading. So people try to make it really complicated. It's all about field containment. And to understand that the fields are established in between the conductors. Let's evaluate now how this board is going to perform with the software. So this board in here is seen with the software, which is a similar software, and it's super simple to analyze the board. Actually, let me close this. So in order to import the board, I need to have the board in OBD++5. So when we are in KitKat, we can convert the board, we can do the file, fabrication outputs, ODB++ file. And we can just convert the board, then we get the zip folder. We are ready to import it already in the software there. So how can we do it? So once we open Simber, we go to File, New Solution. Then we can have an active template, or here we can choose other parameters. But let's keep it simple. Here we choose if we want mils or millimeters, micrometer, whatever we want. I keep it in millimeters. And then we proceed to import the project. So here we name the project, and then we can select in here ODB++ files. Then here is going to ask us to upload the board. Now here I have already imported the board. Like in here, I just select, you see, this is the ODB++ file. I just select, open, and it's going to import the board directly. So I'm not going to do that because I have it already. So I'm just going to open the solution, which is essentially what is going to happen once we import the board. Okay, so once we import the board, then you have something like this. You have the board, you can see how it's constructed. You have the Stackup with the signal. Here you have the links or net. You can see them selected on the software. And then it's going to distinguish already differential pairs. How simple is it to do a quick checkup of the board? So we're going to check, first of all, in here, you're going to have this window here, which is going to tell you exactly what you want to do with this board. So I come in here, and what do I want to check? The first thing that I want to check is the reference integrity violation. So what is going to do this analysis here is going to check if my nets in here, the net that I'm going to select, so if the signal has the reference throughout the whole propagation. So not just in terms of the reference plane, but also when it transitions. So when it goes from horizontal propagation, which is when the signal is going from here to there, but also when it goes in vertical propagation. So when the signal goes, for example, at this point, when it goes from the bottom layer to the top layer, it's going to check, does the signal have the reference in this point? And then the other things that it's going to check is if evaluate the impedance continuity. So does the signal sees the same impedance throughout the whole propagation? Because if it doesn't see the same impedance throughout the whole propagation, then I have the possibility of seeing reflection, depending on how big is the impedance discontinuity. And what's worse for us, when I have the change from differential mode to common mode, in there I can have problems in terms of emission. Because if you have been watching the lesson that I have in the course of radiated emissions, then you're going to see that the common mode currents are much more effective at propagating, because they change basically the way they propagate. Because one is the propagation with a current loop, and the other one is propagation like in a dipole or a monopole. So it's going to check in here the impedance discontinuity. So if the signal has the impedance continuity throughout the whole propagation. And the other thing that I can check in here is the crosstalk noise. So in here I can select how much local coupling threshold I want to select. So for example, here select 10 millivolt, and I'm going to check between this net, the net that I'm selecting here, how much crosstalk there is going to be. So how much coupling of the signal from one net to the other. If I have a signal in here, how much of the signal is going to couple to this? And why this is important? It's important because not only for signal integrity, so that's why I like this software, because it is not just about signal integrity. It's also about, if you understand how signal integrity have an impact in terms of EMC, then you can see what are the possibilities of your board to pass the EMC test. Because you can see how signal integrity affects the EMC results at the end. So for example, if I have in here the coupling of the signal between this net and this net, what can happen here? It can happen that I'm trying to propagate a signal from this net, then it couples to this net, and maybe in here I don't have a cable connected to it, to the connector. Or maybe in here I do have a cable connected to the connector. And so maybe this cable is 2 meters long. So if a signal can couple from this net to this net, what can happen is that then a signal coupled to this net can propagate through the cable that I have connected to this port and to this particular pin. And this cable serves as an antenna structure for the signal. So if I have just a little bit of signaling coupling from this net to this net, I can already have common mode carriers that are trying to radiate out of the board because I have a cable connected in there. So this is also why it's important to have filters, not only for the input, but also for the output. Because if I have a filter in here, placed in the input and output connectors, then I have more chances to stop the signal from propagating outside of the board, even if I have internal cross-coupling. So you see, it's all about fundamentals. We didn't show equations now. We talk about three different things, which are the return and reference plane. The other one is the impedance discontinuity, and the other one is crosstalk. So 3 important things. Now I'm going to disable these 2 because if I keep them enabled, it's going to be like a Luna parking. And I'm going to select these nets. So I'm going to select all the nets in here. So once I select all the nets, then I'm going to just click run, and it's going to run the simulation with the net that I selected for these reference integrity violations. So it creates basically a report for you. So it's super fast to understand where is the problem and how I can fix the problems. So it tells you immediately, where do I have the problems on the board? What type of problems do I have? How many do I have? Where do I have them? And how can I fix them? This is super important. How can I fix also the problems? So how long does it take me to see how the board is going to perform good or bad? This is a laptop. It took not even 5 minutes to run the simulation, probably 2 minutes, 5 minutes through the whole process to convert the board in ODP3+ files, to import it on the software, and then to run the simulations in here with the things that I wanted to check. So in 5 minutes, I can already see what are the chances of the board to pass EMC compliance test. If I understand what I'm checking, obviously. But if I do, I can see already, okay, I have in here this problem in reference integrity. So reference integrity violation. So where do I have the problem? Okay, the problems are divided then in localization breakout. So what does this mean? It means that in here, for example, I have a lack of reference in this point here where I have a localization breakout because I don't have a return reference via. So what does it mean? It means that the signal comes to this point, and once it's in this point, it doesn't have where to reference the field, and then it spreads, and then it changes also the way the signal was supposed to be constructed. So if we think in terms of also of impedance, what is the impedance? The impedance is simply the ratio between voltage and current. So it doesn't have to be more difficult than that. It's a ratio. It's a ratio of the fields, and it's a ratio of how the voltage is in comparison with current. So if I have this change of the impedance because I don't have the stitching via closer in here, this is going to change the way my signal propagates. And it tells you already you have a critical problem. This is a problem where you need to place a stitching via closer because you have a breakout of the reference integrity here. Now you see, look how many problems it found. All in these vias in here, I needed to have a stitching vias close just to contain the fields. At least one, at least. So if I have the signal in here, which is reaching this point, the signal will be spread in two different directions. So the signal is coming and is propagating in this direction. Then it comes to this point, and in here, there is a different impedance. So I already have a reflection in here. How much? I don't know yet. I need to know what's the signal, what's the impedance, but this is things that we can calculate or we can have an approximation. So this is already a problem here. Then it gets to this point, and what the signal has to do is to transition and keep propagating in this direction. So in here, if I have the return reference plane underneath, the fields are going to be established in this way. Of course, I'm going to have also some fields in here, but assuming that the Stackup is right and that this return reference plane that I place on the bottom is close to the signal layer, then the fields will prefer to be established in this way, and I have less fringe fields in here on the top. Okay, but up to this point, the fields are in here. I have the plane underneath. Then the signal now has to go up because it has to transition on the top. So if on the top, I have the other return reference plane, suppose that this is on the top in here. So the Stackup can be also that I have the Stackup like a signal, then I have return reference plane in here on the second layer, and then I have the other return reference plane on the third layer and on the fourth. So the way I'm supposing now the signal is going to propagate is that I have return reference plane on bottom and top, and then I have signal layers in here, okay, in the middle. So it's a signal, and the other one are return reference plane. Okay, so how the field is going to propagate. So when it's on the top, the fields are going to be established between the return reference plane on layer 1 and the signal layer on layer 2. And this is good. This is the propagation of the signal here in between these two layers. Now, the bottom layer is the same. We said that the fields are going to be established here between the return reference plane and the signal layer. So between these two layers. So what happens in here? Now, when the signal has to go from this layer to the other layer, from the third layer to the second layer. So in this point in here where I have the transition, then the fields in here, they want to establish as well the reference that they had before. If I don't place the stitching via in here, then the fields, they just try to spread and couple to the first low impedance structure that they find. So if I have any other copper or metal structures in here, they're going to couple to that. So if I have a signal, like in this case in here, you see, there is this other via, then the fields most likely are going to be established so that I have the reference But then this point in here needs to still close the current loop. So where is this current loop established? It's hard to say, but most likely is not a current loop that I want to have in there. Why it's so important to have the current loop established? Because if I don't control the current loop, if you check in the radiated emission lesson, you're going to see that the current loop is directly proportional to the emissions in terms of differential mode current. So the larger the loop, so the larger the path that the current has to go through, the more area is enclosed by this loop, which means the more radiations I have. So what does it mean? It means that I need to establish in here the reference for the signal when it's transitioning. Why? Because I want to contain this field. So what I can do in here is to place stitching vias right next to the signal via. If I place at least the two stitching vias like this, then the fields are going to be established between the stitching via and the signal via. The signal is still contained, then it comes here on the top, and it is established once again between the top and the signal area. So between the return reference plane and the signal area. Okay. And then I have the containment of the fields. The more stitching vias I can place in there and close to it, the more I can contain the field. So in the course, there is also one of the lessons that talks about specifically about this issue here. Then let's open once again in here the report. So here you can see all these stitching vias, they have all the same issues. And then it tells me also here I have less issues. Why do I have less issues? The severity here is lower because I have this plane in here, but also because I have this stitching via in here close by. So it tells me, look, you still have a problem. You need to move the stitching via a little bit closer, but you're already doing better than before. So it tells me the severity of the problem and then how to fix it in there. So you see it changes. In here before it was moved the stitching via, in here it was added the stitching vias because there is no stitching via. Here is when you're selecting the connector, for example. Look how problematic is this. I have only signal with no return reference plane adjacent. So how are the fields going to be established with it? To whatever structure they can find so that I can establish this here. So this return reference is going to be established no matter what you design in there. Because if it's not established, then you don't have signal propagation. It's as simple as that. So when I have this case in here, if I have signal propagation, then it means that these return reference plane, they're trying to be established in whatever ways they find. So the electric field, like in here, I have the copper plane. So it's going to be established in this copper plane that then is connected to the ground. This means that the current loop that is going to be established is whatever the path it finds in here. So if this is the return reference plane, then the current loop, how is it going to be established? If it's coming from here, this portion of the plane needs to be connected and go back to the source that it came. So the current loop is going to be massive for this. And so again, if the current loop is massive, it means also the radiations are massive. So having in here at least one of the stitching vias connected to the return reference plane is going to be essential. So we cannot just place the signals in here. We need to have a return reference plane adjacent to the signal. Then let's check what are the other problems that we have. Reference discontinuity. So this one is checking, do I have a reference throughout the whole propagation of the signal? And here it tells me, no, you don't. Because when the signal is propagating in this net, for example, you see there is a cutout under or over the trace. So it means that the signal cannot be established in this way. And so what is it going to happen when the signal is trying to propagate? So if I break in here the plane, if I have a cutout, let's suppose that I'm cutting the plane, the blue plane underneath. What happens to the signal? The signal is coming to this point, and then the return reference plane here breaks. So the impedance already changes because the voltage and the current ratio is changing. So also the signal is changing. Then the fields, how they're going to be established, if they can leak from the structure that I created. So if they can leak out from the structure here, then they're going to try to expand and find this coupling path so that they can close the current loop. And so this is exactly what it's telling me there. Here it's telling me you have a cutout under or over the trace. So how can you fix this issue here? And here it tells you, it's very simple. You just need to route the signal over a solid ground plane. When the project manager asks you, how many layers do you need to use for this project in here? You're going to say 2 layers, or at least if it was fairly inexpensive, you would say, I would choose even 3 layers. The problem with choosing 3 layers is manufacturing, because they said, no, if you want to choose the layers, maybe we can do you 3 layers, but it's going to be quite expensive for you because we don't usually do that. We usually do it in pairs. So which Stackup can I choose, which is the cheapest possible, but also the most effective? Because we saw, if I use the Stackup in here, so if I use 2 signal layers without the return reference planes, trying to establish in here coplanar waveguide, which are not coplanar waveguide, then what can I choose? Because if I try to use this board, I have no chances of passing EMC test. So I can choose a 4-layer design. Now, the problem when there's in projects that call that tells you, oh, you need to choose the cheapest possible board, your answer should already assume that it's a 4-layer. Why? Because if you can route everything on the top or on the bottom, if you can have all the signals routed on the top trace or the bottom layer, then you can say, look, I managed to route all the signals only on 1 layer, and I can use the second layer as a return reference plane. So we can have a cheaper stack than what I thought. If you cannot achieve to route all the traces on the top or on the bottom, then you have 2 signal layers that you're using and 2 internal layers or external layers that you can use as a return reference planes. But still, this is the cheapest combination possible. And we'll also ensure that you're not going to spend thousands of dollars when you go and do the EMC test and you fail, because this is a guarantee for failure. And so it's still the cheapest possible Stackup. Okay, so you see in here, it tells you route this signal because there is no reference adjacent to it. So the other things that it's going to check, trace impedance. You see, it tells you in here, you have a critical issue because this net in here, so we were checking in here for 50 ohm impedance. Now, suppose that you have to keep 50 ohms or you want to choose something else, like you need to have a net that it needs to be routed with 75 ohms impedance. So the software can check, you see in here, the target impedance is 50 ohm. So it's going to check for the whole propagation of the signal. Is the signal going to see 50 ohms or not? And it tells you in here, you don't have 50 ohms. In fact, in here, you have 100 ohms in this point. And so how can you fix this issue here? You can just increase the width so that you decrease the impedance. So this is super awesome because you just run the simulation. It tells you, there you go. This is the problem that you have in here. In this board, is 2,610 problems of trace impedance. So just from trace impedance. Then look at the problem in here of localization breakout. So when you don't have a stitching veer close to it, this is 25. Look at insufficient number of stitching veers, 16 problems. But look at the reference discontinuity, 433 problems. Trace impedance, it's a massive number. So when we're choosing how we need to route even a simple board like this, if you don't have the requirement to have a specific impedance, I just simply go for 50 ohms. First of all, today you can check even with AI or internet, you can just check what kind of impedance do I need to have for this type of nets. So if I have USB, what is the impedance that I need to have? If I have DDR3, what is the impedance that I need for this net? And you're going to find it out immediately. And so once you know what is the impedance that you need to maintain for the whole signal propagation, you can simply design the traces with this impedance. The impedance, so we said that there was a ratio between voltage and current. So how is it going to be calculated? It's going to be calculated between the structures that you have. So if you don't have in here the return reference plane, how is it going to be calculated the impedance? is going to be calculated with the next structure that you have. So between the top and the bottom layer. So the impedance in here is calculated between this net in here and the other structures that you have around. Because it's going to check, okay, when the signal propagates in between the stack-up, so in between layer 1 and layer 2 in this case, what is the impedance that is going to see? And this is based on the distance, on the geometries of the board that you design. So you can choose already how this impedance is going to be. So if you want it to be 50 ohms, you need to make sure that whatever structure you have adjacent to it is going to guarantee that you have 50 ohms throughout the whole signal propagation. So in here, in this case, it's simple. If you use a return reference plane, then you just measure, okay, what is the trace width, what is the distance, and this, once you put it in the calculator, there's plenty of pre-calculators online, so you can check it easily, or even in this case in KiCad, but even Ultimate Designer, which, by the way, integrates the Simber calculator, and it tells you exactly what is the impedance when you choose the Stackup. If you're choosing the Stackup, you have, let's say, 4-layer board. Then it tells you if you want to achieve a 50 ohm impedance between your signal faces and the return reference plane, then you need to have this trace width. And it's calculated based on the geometrical structure that you have in the board. And you see here it tells you increase the width. Like in here it tells you reduce the width. In here it's telling me, look, you wanted to have 50 ohms, but in here you have 24 ohms, 24.9. So in here what you have to do if you want to have 50 ohms is to reduce it. Now, what about crosstalk? Crosstalk in here, we have 355 issues, 355 violations we have in here. Look at how simple it is going to be to find the problems. So in here, it tells me, look, you have this problem in here. You have a violation of crosstalk because you have a signal. You wanted to have the target, the crosstalk in here, which was 10 millivolts, but you actually have 15.53 millivolts. So if this is going to create a problem for you, then you need to increase the distance between the signal traces. So that's why you see all the things that we just discussed in here, they can be fixed with placing a return reference planes adjacent to the signal layers, increasing the distance between the net, so increasing the distance between these two traces. And then the other one is placing the stitching vias. And the fourth one is by keeping consistency with the nets when I choose the width of the signal traces. So if I change when the signal is propagating from this trace, if I suddenly change the width of this net, this is going to change the impedance, which means it's going to create the problems in terms of impedance discontinuity, and it can cause reflection. So these 4 basic things, they already determine 90% of the behavior of my board in terms of EMC, but also signal integrity. And we didn't use any crazy formulas. We didn't go to calculate triple integrals and things like that. It's just a basic concept of electromagnetic fields. And most importantly, we didn't talk about electrons. None of this stuff. We just talk about field containment and the ratio between the field. So the ratio between the voltage and current. That's it. So see, increase the distance. Here it tells me, look, you still have some problems here. Why also do I have this problem? Because I don't have the reference. So if I don't have the reference, then when the reference is going to be established, it's going to be established between these nets. But look at the current loop in here. Suppose that this signal here is my signal layer. And now this is used as a return reference for the signal. So we're talking again this scenario here. So this is the signal, and this structure in here is the return reference. So how is the current loop? Let's suppose that the signal is trying to propagate and go to the other side. So from left to right. So once it's in here, then I have the current loop, which is essentially like this. So if I know that the radiated emissions from differential mode current are related to the area enclosed by the loop, look at the area that this loop is enclosing. Then I can put this one in the formula and I can calculate this. So you can calculate even just by looking at this current loop, what is going to be the emissions from your board, from differential mode current. Now, the other problem that this is going to create is that when it's trying to establish this reference, so when the reference is trying to be established between the signal layer and the return and reference. In here, I'm going to have as well a certain impedance. So this impedance here is what is going to create me the common mode issues, because as the fields propagate in here from this point to this point in the form of displacement current, then all of a sudden I have a voltage drop. So I have a voltage drop. This voltage drop is going to drive the common mode currents, which if I have this board connected to the cables and I had this voltage drop in there, suppose that this cable is too long, here I had this tiny voltage drop driving the common mode current. So what is going to happen here? It becomes the voltage source for the common mode current, and then these common mode currents, they will radiate their energy outside of the board. Now we know the common mode currents, even a few microamps of common mode currents, they don't allow you to pass the EMC test because they are so effective at radiating. So this is how problematic this can be. Why? Simply because I didn't have a return reference plane there. And all of a sudden I have this crosstalk, I have these impedance discontinuities, I have these reference integrity violations, all these issues in terms of signal integrity, which then translate in EMC problems. So if you have the PCIe links in here, you can, for example, import already the settings, and the software is going to make this measurement with the settings that you imported. So if you have PCIe, it's going to check, okay, if I have the PCIe net in here, how is it going to perform? Because now I just show you the basics. So this is just for reference, crosstalk, and also for impedance discontinuity. But if you want to, then you can check also, how is the signal? What are the reflections? How much reflection do I have? So you can simulate all of that. You can see the eye diagram. So it goes much more in depth. And also, if you localize the analysis, then you can see how the fields will spread. So if you choose a certain Stackup, you can simulate how the fields in between. So how the magnetic field, the electric field, displacement current, and the power flow. So it gets much more powerful than that. But from the EMI point of view, so from a basic EMI point of view, these three things is all you need to begin with. So if you know already these three things, you can already cover 90% of the issues, because then the rest, it becomes more of an issue of how did I place the cables? How did I place the components? So do I have the board, the partition or not? But these are, I would say, these are second stage issues. The most important are those. And these are the most common ones. I promise you, if they give you a board that is failing for EMC test, check these three things. Now I show you with the software, but you can check them even without the software to have an initial understanding. Because with the software, it's faster. It takes you 5 minutes to have the result, the report, you print the report. Okay, this is what you need to do. Now, if this is $1 million project, suppose that this board is not passing the EMC test. They contact you and they say, look, I need an EMI specialist. They check my board because I cannot pass the EMC test. I try multiple times. I don't know what to do. You plug it in here. In 5 minutes, you have already most of the issues that you need to fix. Or board in here, it might be several millions. I don't know how much it's worth to this project, but it's probably several million. Each day that you're not on the market, you're losing money. So if you don't pass the EMC test, you cannot sell, which means you are losing money because you're not on the market. And so in 5 minutes, you can find what are the issues that you need to fix and how to fix them. So this is why I love this software so much, because in 5 minutes, you can find exactly what you need to do. This is strategy, like these are the issues that you have. You can measure them. This is the problem. You can calculate how much is it going to have an impact on my system. And with the 5 minutes of your work, you can fix already multi-million-dollar projects. Just because you are able to unlock these 4 problems here. Reference of the signal. One is the horizontal propagation. The other one is the vertical propagation. Then you have impedance discontinuity. And the fourth one is the crosstalk. So if you're able to fix these 4 issues, you can already unlock multi-million-dollar projects. And people want to complicate this with the crazy math or this and that. Even the Maxwell's equations. When you look at the Maxwell's equations, you need to understand, what do the Maxwell's equations mean? What are these ratios there? How the changing of the electric field is going to mean that I have this magnetic field propagating. just to evaluate. You don't need to have the exact calculation at this point, but if you don't understand the principle and the fundamentals behind it, doing the calculation is going to lead you to wrong results because you don't even know what to expect. Now, I think that you can download the simulation software when you go to simberium.com and you have trial operation, if I'm not wrong, for free. So you can even try that. If you enjoyed this live masterclass recording and want to participate in a future session or ask questions, you can join us at the Academy. Just go to freddoelectronics.com and there you will find information on joining the Academy along with resources to help you with EMI, EMC, and PCB design.